When I look out into the universe, I am not just seeing distant objects. I am seeing a record of how space-time has been stretching over time. The surprising part is not that the universe is expanding. The surprise is that the expansion is speeding up. To understand what that means, I start with a simple idea. In an expanding universe, distances between galaxies grow even if the galaxies are not moving through space in the usual sense. Space itself is changing. This is not an explosion into empty surroundings. It is a change in the scale of the universe, described by a number called the scale factor. When the scale factor grows, the typical separation between galaxies grows with it. We measure this expansion using redshift. Light from a galaxy is stretched as it travels through expanding space, so its wavelength increases. That shift toward redder wavelengths tells us how much the universe expanded while the light was on its way. Redshift on its own does not give the full story. I also need distances. For nearby galaxies, we can build a distance ladder using geometric methods and well-calibrated standard candles. For faraway galaxies, we rely on objects whose intrinsic brightness can be inferred. This is where Type 1a supernovae enter the picture. These are explosions of white dwarf stars in binary systems, and they have a characteristic peak brightness after careful calibration. They are not perfectly identical, but their light curves let us standardize them well enough to measure cosmic distances. In the late 1990s, teams used these supernovae to map how expansion changed with time. If gravity from matter were the only major influence, the expansion should have been slowing down. Instead, the distant supernovae were dimmer than expected. The simplest interpretation was that the universe expanded more than it should have in a purely matter-dominated cosmos. Expansion was not decelerating, it was accelerating. Calling this effect dark energy is a label, not a full explanation. It means there is something in the energy budget of the universe that makes the expansion speed up. In general relativity, gravity is not only sourced by mass, it is sourced by energy density and pressure. That is a key point. For normal matter and radiation, pressure is zero or positive, and gravity tends to slow expansion. But if a component has sufficiently negative pressure, it can make the expansion accelerate. The cleanest mathematical form of that idea is the cosmological constant, often written as lambda. In Einstein's equations, lambda acts like a constant energy density built into space-time itself. If that is what dark energy is, then its density stays nearly constant as the universe expands. Matter thins out as space grows because the same amount of matter spreads through a larger volume. Dark energy in the form of a cosmological constant does not thin out in the same way. That means it becomes more important over time. Early on, matter and radiation dominated. Later, dark energy took over and started driving accelerated expansion. I want to be careful here. Accelerated expansion does not mean galaxies are being pushed through space by a force like a rocket engine. It means that the scale factor is changing in a way that increases the rate at which large separations grow. Locally, gravity still wins. The Milky Way and Andromeda will still fall together. Galaxy clusters can remain bound. Dark energy shows itself most clearly on the largest scales, where the average density is low and the universe is close to uniform. So how do we know this is real beyond supernovae? The strongest support comes from multiple lines of evidence that fit together in a single model. One is the cosmic microwave background, the afterglow of the hot early universe. It carries a pattern of tiny temperature variations. Those variations are a snapshot of density ripples when the universe was about 38,000 years old. The angular scale of the main acoustic peak in that pattern tells us about the geometry of the universe and the distance to that early surface of last scattering. Observations show the universe is very close to spatially flat. In a flat universe, the total energy density must be very close to a critical value. When we add up the matter, we can infer it falls short of that critical density. Something else must fill the gap. Dark energy does that in the standard picture. Another line of evidence comes from baryon acoustic oscillations. In the early universe, matter and radiation formed a coupled fluid. Sound waves traveled through it. When the universe cooled enough for atoms to form, those waves froze in place, leaving a preferred scale in the distribution of matter. Today, that scale shows up as a small bump in the correlation of galaxy positions. It acts like a standard ruler. By measuring it at different redshifts, we can trace how the expansion rate changed over cosmic time. Those measurements agree with an expansion history that transitions from matter-dominated deceleration to dark energy-dominated acceleration. A third line comes from the growth of large-scale structure. Gravity makes overdense regions grow over time. The rate of growth depends on how fast the universe expands. Faster expansion makes it harder for gravity to pull matter together. So by measuring how clumpy the universe is at different epochs, using galaxy surveys and weak gravitational lensing, we can test whether the expansion is accelerating and what kind of dark energy could be responsible. Again, the results are broadly consistent with a cosmological constant-like component, though there are tensions and uncertainties in the details. Now I need to bring in dark matter, because dark energy is not the only unseen ingredient. Dark matter is inferred from its gravitational effects. Galaxy rotation curves stay flat at large radii, which implies more mass than we see in stars and gas. Galaxy clusters have more gravity than luminous matter can provide, seen through galaxy motions, hot X-ray gas, and gravitational lensing. The cosmic microwave background also tells us the amount of matter that can clump. It points to a universe where most matter is dark and cold, meaning it moved slowly when structures began to form. Dark matter and dark energy play very different roles. Dark matter clumps and forms halos. It deepens gravitational wells and helps galaxies and clusters form. Dark energy does not clump much, at least not in the simplest models. It acts more like a smooth background that affects the overall expansion. In the standard cosmological model called lambda CDM, the lambda is dark energy as a cosmological constant, and CDM is cold dark matter. This model fits a huge range of data with a small set of parameters. That success is real and important. But it is not the same as understanding what dark energy is. So what do we actually know about dark energy? Observationally, we know the expansion is accelerating. We know dark energy contributes about 70% of the current cosmic energy density, with dark matter around a quarter and ordinary matter only a few percent. We know that whatever dark energy is, it is very smooth on large scales. We also know that its equation of state parameter, called W, is close to -1. This parameter relates pressure to energy density. A cosmological constant has W equal to -1 exactly. Current measurements are consistent with that, within uncertainties. What remains unknown is the physical origin. If dark energy is a cosmological constant, then it may be vacuum energy. Quantum field theory predicts that empty space has energy from fluctuations. But naive estimates give a value that is enormously larger than what we observe. This is the cosmological constant problem. It is not a small mismatch. It is one of the largest gaps between theory and observation in all of physics. We do not have a widely accepted solution. There are other possibilities that stay within known physics frameworks. Dark energy could be a dynamical field that changes slowly over time, often called quintessence. In that case, W could differ from -1 and could evolve with redshift. Another possibility is that general relativity might need modification on very large scales. If gravity behaves differently across cosmic distances, it could mimic accelerated expansion without a separate dark energy component. But modified gravity models must also match the tight constraints from the solar system, from gravitational waves, and from the detailed pattern of structure formation. That is a high bar. I also want to address a common confusion. People sometimes hear that dark energy is repulsive gravity. In general relativity, it is more precise to say that a component with negative pressure changes how the expansion evolves. It does not act like a force that pushes objects apart locally. The mathematics is in the Friedmann equations, which connect the expansion rate to the contents of the universe. In those equations, acceleration depends on energy density plus 3 times pressure. If pressure is negative enough, the combination becomes negative and the expansion accelerates. Here is a thought experiment I find useful. Imagine a universe filled only with matter. As it expands, matter density drops, gravity weakens, and the expansion slows. Now imagine adding a constant energy density that does not dilute. As the universe grows, matter becomes less important, but the constant energy stays the same per unit volume. Eventually, the constant term dominates the equations. At that point, the expansion approaches an exponential-like behavior. That is close to what a cosmological constant produces. The key is not that expansion becomes fast everywhere at once, but that the rate stops slowing and begins to speed up in a specific, predictable way. This brings me to the fate of the universe. If dark energy is a true cosmological constant, then the expansion will keep accelerating. Distant galaxies will cross a horizon where their light can no longer reach us because space between us and them expands too quickly. Over very long times, the observable universe becomes more isolated. Locally bound systems remain. But the large-scale structure beyond our local group gradually fades from view. If instead dark energy changes with time, the fate could differ. If it weakens, expansion might return to slower growth.